Okay, let's unpack this. Welcome to AI Peer Review, where we shortcut your path to being well-informed. Today we are diving into what looks like, well, a pretty fundamental architectural revolution in vision language models,
It really is. We're talking about a move away from the world of token generation.
which is costly, time-consuming.
Exactly. And into this highly efficient domain of continuous embedding prediction.
Our subject is VL-JEPA, the Vision Language Joint Embedding Predictive Architecture.
And the sources we looked at detail a really controlled experiment. They showed that if you change the model's goal from predicting discrete words,
Yeah,
text tokens,
right.
to predicting these abstract, continuous semantic embeddings, you just fundamentally rewire the VLM for speed and for efficiency.
So our mission today is to get to the bottom of why. Why is this shift not just, an incremental improvement, but a real paradigm change?
And the numbers are pretty compelling.
They really are. VL-JEPA gets stronger performance with 50% fewer trainable parameters. That's half.
And for real-time video, this is the kicker, it enables something they call selective decoding.
Which slashes the decoding operations by a factor of nearly 3. So let's start at the beginning. Why are the classical VLMs so inefficient in the first place?
Well, to really appreciate the VL-JEPA breakthrough, you have to understand the major bottleneck that's just inherent in the standard approach.
You mean models that rely on autoregressive token-by-token decoding?
Exactly. Think of the big ones like Instruct BL-UP or some of the QuenVL variants. They have two massive and related drawbacks.
And the first one is training cost, right? The sheer redundancy that's built into the process.
Yes. When you train a VLM to generate a specific sentence, let's say a dog running on a grassy field,
Yeah.
it has to learn not just the core concept,
The dog running.
the dog running.
Yep.
It also has to capture all these task-irrelevant sort of surface linguistic features.
So word choice, style, different ways of paraphrasing it.
It's essentially modeling noise. The model is forced to spend all this unnecessary computation trying to distinguish between a dog running on a grassy field and, say, a canine sprints across the lawn.
Semantically, those are almost identical.
They're identical. They convey the same high-level idea. But in the discrete world of tokens, they're treated as two completely distinct, highly complex sequences.
So if the model's job is to output the concept of a running dog, it currently has to learn thousands of different phrases for it, which are all mathematically miles apart in that sparse token space.
That is the core problem. It's orthogonality in the raw token space.
Yeah.
The text outputs are just entirely different strings of words, forcing the model to capture all these disjoint regions in its probability distribution.
Even though we only want one single abstract concept.
Right. VL-JEPA just flips this on its head. Instead of making the model predict the physical address, the exact token sequence, it trains it to predict the GPS coordinate of that concept in semantic space.
That makes the training goal so much cleaner, almost unimodal. But what about the second drawback of the classical models? The practical issue of speed.
Latency. And that is absolutely critical for real-time applications. If you're building a smart system that needs to track live action, say, recognizing a key move in a sport, you need sparse, selective outputs.
You don't need a constant stream of text describing every single frame.
No. But because classical VLMs are locked into this autoregressive decoding, they are fundamentally stuck generating token by token. You have to wait for one token before you can generate the next.
And that compulsory latency just makes them a poor choice for any kind of responsive, low-overhead system.
It does. So if token generation is slow and it's redundant, VL-JEPA's solution is to just sidestep that entire output mechanism during training.
And focus purely on the latent semantic space.
Precisely. It turns the expensive task of predicting text into the highly efficient task of predicting meaning.
Okay, so let's get into the weeds of how they built this. It's a 4-component architecture. What are the roles here?
At a high level, the system splits into the encoders, which turn complex data into simple embeddings, and then the predictor, which links them.
Okay.
So we start with the X encoder. This is a powerful, pre-trained vision component. Its job is to take the visual input, an image or a video, and just condense it down into a compact, fixed-length visual embedding. That's the foundation.
Then you've got the Y encoder. This handles the text target.
Right. It takes the ground truth text, let's say a dog sprints across the lawn, and it maps that to an abstract, continuous target embedding.
So it's essentially translating that sentence into the pure concept of what? Running dog?
Yes, and that is its critical job. It abstracts away all the irrelevant linguistic details, the synonyms, the style, to create that single, compact, semantic representation.
So the encoders create the inputs that the third component uses,
Mm-hmm.
which is the predictor. And this is where the real learning happens.
This is the core. It's a transformer-based network that learns the functional relationship. So given the distilled visual knowledge and a specific text query, like a question.
It learns where that concept should land in the semantic space.
Exactly. It outputs the predicted target embedding.
And this leads to maybe the most important efficiency gain. The fourth component, the Y decoder, is totally separate.
Completely separate. It is only called during inference and only when you absolutely need a human-readable text output. It is not part of the main training loop at all.
But wait a minute, if you're training the model to predict an abstract embedding, how do you stop that from just becoming generic or losing nuance? If it never has to generate actual tokens during training, how does it know how detailed the concept needs to be?
That is a critical question, and it speaks directly to the advantage of this continuous space. Remember the example from the paper, the lamp is turned off versus the room will go dark.
Right. Both are plausible answers for an image, but tokenically they're completely different.
And hard to learn.
Yeah.
In the embedding space, the Y encoder maps both of those plausible answers into an extremely tight cluster, a small, defined semantic neighborhood.
So the learning target becomes this compact, well-behaved, unimodal distribution.
Right. The predictor doesn't have to learn thousands of ways to hit an answer. It just has to learn where that single cluster of meaning sits. It simplifies the prediction task dramatically.
So it inherently pushes the model towards a higher level semantic understanding, not just surface level text replication.
Exactly.
So the training objective then is to minimize the distance between the predicted semantic coordinate and the ground truth one. How do they stop the model from just learning to predict a single average embedding for everything? I think it's called representation collapse.
That's where the loss function comes in. They use something called info-ins e-loss. It's pretty standard and contrastive learning, but it plays a crucial role here.
Okay.
So imagine you have a big batch of training examples. InfoNC doesn't just try to make the correct pair of embeddings similar, it also actively forces the incorrect pairings in that batch to be dissimilar.
So it's not just pulling the right answer close, it's actively pushing all the wrong answers far away.
That's it. This is the uniformity regularization part. It prevents representation collapse by making sure the embeddings are spread out uniformly across the entire semantic space. It maintains distinction and nuance.
It's like a continuous quality control.
A perfect way to put it.
Okay, that makes perfect sense. So moving past the theory, let's look at what this actually means for speed and learning capability. They ran a very strictly controlled comparison. What did that show about sample efficiency?
The comparison was really rigorous. VL-JEPA's predictor was about 500 million parameters.
Okay.
And it was matched against a classical VLM baseline with a 1 billion parameter LLM backbone. And they used identical vision encoders, the same data, same training iterations. The only variable was the objective.
Embedding prediction versus token prediction.
Yes.
And the difference was, well, pretty striking, especially in how quickly the models learned.
VL-JEPA showed significantly higher sample efficiency. After only 5 million samples, which is a relatively small data set, VL-JEPA had already achieved a really high-quality score, 14.7 CIDR.
And just for our listeners, the CIDR score is a key metric for image caption quality. Higher score means the caption is closer to what a human would write.
That's right. And its top 5 accuracy was already at 35.3%.
Meanwhile, the baseline VLM, which was twice the size in trainable parameters, was lagging way behind.
Significantly. It hit only 7.1 CIDR and 27.2% accuracy. It just validates the core hypothesis. Training in the continuous embedding space lets the model learn the core concepts much, much faster. It's massively data efficient.
So this brings us to the second huge practical efficiency gain, which is inference speed for live data. While the total time to generate a full sentence might be similar, VL-JEPA offers something the autoregressive models just can't: decoupling.
And that decoupling is the secret sauce for online applications. The heavy lifting processing video frames running the predictor to get that abstract embedding is extremely fast. They clocked it at around 126 milliseconds.
While the 200 plus milliseconds needed for generating text, the slow part is totally optional.
Entirely optional.
And this is where selective decoding comes in, which is probably the most exciting practical feature for, smart devices or live monitoring.
Oh, absolutely. Traditional VLMs, they're forced to decode text every single time.
Right.
Or risk missing something important.
Right.
But since VL-JEPA produces this continuous, non-autoregressive stream of semantic embeddings, you can just monitor that stream constantly with minimal lag. The system just waits.
Waits for what? What's the trigger for the system to actually pay the cost of decoding the text?
It monitors for significant semantic shifts. So if you're tracking video feed, the system can calculate the variance or the distance between the current embedding and the ones from the last few frames.
Okay.
And if that local window variance goes above a certain threshold, meaning the visual situation is abruptly changed, that is when the system triggers the Y decoder to give you a human-readable update.
So if I'm tracking a car, the model doesn't constantly generate the blue car is moving, the blue car is still moving. It only outputs the blue car has stopped the moment that semantic embedding shifts dramatically.
Exactly. They tested this on real-world streaming data from the Ego Exa4D validation set.
Which involves complex action tracking.
Very complex. And they found that this adaptive selective decoding strategy achieved the same level of performance as uniform forced decoding while requiring 2.85 times fewer decoding operations.
That's a true Pareto improvement. Better responsiveness and less computational load at the same time.
It's a huge deal.
Genuinely groundbreaking for, energy-constrained edge devices. But the architecture isn't just efficient, it's also a unified generalist. That's the next fascinating point. This single architecture handles 3 fundamentally distinct tasks without any structural changes.
The shared latent space just makes multitasking natural. The architecture natively supports, 3 pillars of vision language processing. First, generation tasks captioning, VQA, that rely on that selective decoding we just talked about.
Then second, discriminative tasks, so like open vocabulary classification or picking the right answer from a list.
Yeah, for those, the candidate labels themselves are encoded into their own embeddings. The system just compares the predicted embedding to the candidate embeddings and picks the closest semantic neighbor. It's a distance measurement problem.
Not a probability distribution problem.
Exactly.
And the third category is retrieval, finding relevant video clips from a text query.
Which is straightforward because everything is already in that shared multimodal embedding space. You encode the text query and you just rank the video embeddings by their similarity. The one model structure gives you the retrieval power of older SIA lifestyle models and the generation power of modern VLMs.
And the benchmark results really underscore this. Even the base VL-JEPA model, with only 1.6 billion parameters, shows remarkably strong zero-shot performance.
It's a massive data efficiency win. The VL-JEPA-based model got a higher average accuracy and recall at 1 across a bunch of data sets than a baseline that saw 86 billion training samples. VL-JEPA saw a mere 2 billion.
It's doing more with exponentially less data. And when you look at specialized tasks, the efficiency leads to some surprising strengths, particularly in world modeling.
Yes, the sources highlight performance on the World Prediction WM task. This task is about identifying actions that logically explain how the world changes in a video.
Like seeing a dirty floor become a clean floor and choosing mopping as the action.
Exactly. And VL-JEPA achieved a new state-of-the-art accuracy here. It surpassed even frontier LLMs like GPT-4o, Claude 3.5, Gemini 2.0. That is huge for physical world understanding.
For visual chain of thought, yeah.
This strong result suggests that predicting into the continuous semantic space forces the model to learn a cleaner, more robust, and more causal representation of how the world works. It's learning the underlying rules, not just descriptive language.
Let's quickly touch on a few insights from their ablation studies. They seem to confirm which components were most essential for these gains.
The initial query-free pre-training stage, that was absolutely non-negotiable.
That's the foundational step where they just establish that basic vision-language alignment.
Right. And dropping that stage caused classification accuracy to just plummet by over 20 points. You cannot skip that fundamental grounding.
And what about the Y encoder itself, the component that translates text into concepts? It seems to get more robust through this JEPA training.
It did. They tested its resilience on some hard negative text comparison benchmarks, things designed to confuse a model with very similar but semantically distinct phrasing. The VL-JEPA Y encoder was far more resilient than comparable encoders.
Ingesting the JEPA method helps create stronger, more abstract semantic representations.
Ones that don't collapse under pressure. Yes.
So let's tie this all together. We've seen that shifting the prediction target from discrete tokens to these continuous semantic embeddings gives you a three-pronged advantage. Higher sample efficiency, a unified architecture for generation, discrimination, and retrieval, and most importantly for real-time apps, massive gains through selective decoding.
The core insight is that VL-JEPA really validates the latent space approach. It's a hyper-efficient path for basic vision language understanding. It proves we can abstract away the linguistic noise without sacrificing performance.
Right.
But we have to acknowledge that for the really complex tasks multi-step reasoning tool use agentic planning, the current state of the art often still resides with the large token generative models.
And this raises a fascinating and I think really important question for the future of AI. If VL-JEPA has shown us how effective it is to conduct simple prediction within this continuous, compressed, multimodal embedding space, what does this unlock for high-level latent space reasoning?
Hmm.
Can we evolve complex visual chain of thought methods, which right now rely on slow, discrete text, to operate directly within this fast, continuous semantic space? That is something for you to mull over as we move toward the next wave of model architecture.